the presentation is all about the history of the atom. Just as a start, we're going to look at how the process of chromatography works. So look at the diagram. You might want to pause the video just to take a couple of minutes to have a look at the diagram and see if you can refresh memory, and we'll get to it in a second. Okay, hopefully there's a few bells then. So you can see typical chromatography with some sort of beaker or container with solvent in the bottom. This is usually water, but it could be something else. You then have photography paper suspended with a base line drawn. Now, often for the exam, the one you state that that's drawn in pencil rather than pen, because pen contains ink, and that could be separated by solvent pigment in the ink and therefore affect it. So, pencil line quite often drawn. The chromatography paper has to go into the solvent, making sure that the pencil line is above the level of the solvent. And other factors to note, it's not on this diagram, but quite often an exam will show the lid of the container, and that lid is there to make sure that no solvent evaporates. And just look at this, you can see the solvent moves, say that chromatography works, passes through the pigments, it dissolves the pigments, carries the pigments through the paper. We refer to the liquid or solvent as the mobile phase and the paper stationary phase. We can see a mixture one here. It's a mixture of this blue dye number 1 and red dye number 3. And the more soluble dye is the red as it's been carried further up the paper. So in terms of today and this presentation, we're going to be looking at models of the atom and how they've changed over time. So for grade 3, just simply recall how ideas about the atom changed over time. For a grade 4, we're progressing on from a equal idea, and we're looking at descriptive type answers, where we describe experiments that have been made out to look at key features. And for a grade 4, a grade 6 plus, it's looking at how and explaining how the experiments that were carried out were able to prove the existence of subatomic particles and that evolution of the model over time. Why do we need to know? It's very important to know about how the atoms change. It underpins a lot of science, atomism, and how it's changed. But the key thing, I guess, we're thinking about here is the purpose of experimentation and the gathering of evidence. As scientists are always looking to carry out experiments in order to gather evidence, and then that evidence could be used to prove or disprove something in science. So it is a vital process of experimentation. It also allows us to gather information about things that we can't necessarily see. Things like atoms, we can't see them because they're so small. So experimentation allows the development of models which we can use to develop our knowledge and understanding even further. So if we go back, I've called it the olden days. What I'm talking about is the ancient Greeks. They were the first to have ideas about particles and atoms, but it wasn't until sort of the early 1800s that there was any sort of substance to this. The Greeks thought that everything must be made of something, but didn't really flesh it out. But the 1800s, it really started to take off with experimental evidence being gathered, so that we knew more about the existence of the atom. John Dalton was the first person to sort of suggest this. He suggested that all substances were made up of tiny spheres and that each element had its own tiny spheres or atoms. So a lump of tin would be made of nothing but tin spheres or tin atoms, and they'd all be identical. A lump of iron would also be made of tiny spheres, but those tiny spheres would be different to the tin ones. And these were sort of the building blocks of nature. He also suggested, though, that these atoms could be rearranged and recombined. So we'd started to think about compounds. So, for example, we know that water is a compound of hydrogen and oxygen atoms that are chemically joined together. So that would sort of back up what Dalton was saying. Okay, what I'd like you to do, last 200 years we have proved experimentally, or the scientists have proved experimentally, the existence of protons, neutrons and electrons, and have developed this atomic idea. I want you to use whatever you've got at your disposal, whether it's laptop, mobile phone, textbooks, revision guides, and have a go at these 4 tasks. And then what we'll do is we'll go back through them and I'll make sure that you've got everything that you need. So task number 1, I'd like you to name the scientist who discovered evidence for electrons and explain how he was able to do that. I'd like you to say how Geiger and Marsden provided evidence for the nucleus. What I will say with this one, you might see the name Rutherford, Ernest Rutherford referred to a lot here. He was sort of the director of these two, Geiger and Marsden, so he sort of directed them to do it. So sometimes you'll see this work referred to as Geiger and Marsden's work, but other times it will talk about Rutherford's scattering experiment. The third thing is Niels Bohr and how he provided evidence for the electron shells. And finally, how evidence for neutrons was discovered. So you probably need about 4 to 5 minutes on each of these. So if you pause your video now, take about 15 to 20 minutes and try and find some information for these. And then when you press play, I'll go through each of these in turn and there'll be a few questions relating to them. So if you want to pause now and try and find this information out. Okay, looking at the first one then, electrons and atoms. J.J. Thomson was sort of the individual who discovered the electron. He discovered that the electron was this tiny negatively charged particle with a mass 2,000 times smaller than the lightest known atom, hydrogen. Basically, you've seen, if you've watched the atomic structure presentation, we actually say that the electron has a mass 1/1840th of that of a proton, and hydrogen is essentially a proton. So it's a very, very small particle. The way he found this out was by applying high voltages to gases which were at a low temperature in a tube. And he found that a beam of particles was sort of produced, and that was attracted to a positively charged plate. Now, if you think back to the atomic structure and charged particles, we know that there are positive protons and negative electrons now. And what these beams of particles suggested, because they were being attracted to a positive charged plate, they must have been negatively charged because opposites attract. Thomson called them electrons, and he said they came from the atoms in the tube. Now, at this time, scientists felt that the atom was the simplest thing and you couldn't split it any further. So what he said is that those negatively charged particles or electrons must be embedded in a positively charged cloud, and they must be the same in balance. So whatever the value of the positive charge be would be offset by the negative charge. And that's because atoms have no overall charge. There is balance. This electrostatic attraction is balanced. The positive charges must be equal to the negative charges. And this is the experiment he did. So this is just to show you. Here's the tube with the gas in it. High voltage applied, kept at low temperature, and the beam that appeared being pulled towards the positive plate. Okay, and being repelled from the negative plate. And this is the plum pudding model he came up with, this idea of a ball of positive charge with little individual negative charges stuck in the positive charge. He called it a plum pudding model, because at that time that would sort of be the pudding that they would talk about, a plum pudding with pieces of plum in it. If we were bringing it up to 2020, we'd probably call it something like a blueberry muffin model, where the little electrons represent the sort of little pieces of blueberry stuck in the muffin. It's just to help you get a bit of a better understanding. Moving on to the evidence for the nucleus then. This was the work of Geiger and Marsden, under the sort of tutelage of Rutherford. They discovered the nucleus 10 years after Thomson. So they fired densely positively charged particles, alpha particles. So what we know from radioactivity, these helium nuclei with 2 protons and 2 neutrons, and they were firing them very densely at a sheet of gold foil, much like tin foil you have in your kitchen, but obviously made of gold rather than tin. They expected the particles to pass straight through. The results sort of surprised them a little bit, because while most of the particles did pass through, some of those alpha particles deviated and changed course slightly, and others were actually reflected back from where they came. And what the results basically suggested was that the majority of the atom was empty space, but with a little positive charge concentrated in the center of the atom, the nucleus. And what was happening was these positive alpha particles, if they came too close to the nucleus, they'd just get deflected, because obviously like charges repel. So the positively charged nucleus would repel the positively charged alpha particle. And if it came too close and hit it directly, then it would repel it back from the direction it came. So they felt, Geiger and Marsden and Rutherford, that the atom was predominantly empty space with a sort of positive nucleus in the center, and then electrons all around the positive nucleus. And this is the experiment you can see. So there's the alpha source being fired out, going through the gold foil, passing through, some getting deflected. So if we look here in diagram B, of the 6 alpha particles shown, 4 of them pass straight through. One of them here comes so close to the nucleus that it just gets deflected slightly, the positives of the nucleus in the alpha particle deflecting, whereas this one comes so close it hits the nucleus directly and the positive charge pushes it back from where it came. Electron shells are next. This was the work of Niels Bohr, and he noticed that light was given out when an atom was heated. We say that the atom's been excited. So he heated the atom and light was given out. And that light corresponded to specific amounts of energy. And what Bohr suggested was that the electrons, rather than just being in a cloud around the nucleus, as Geiger and Marsden said, the electrons must be in shells that are at set distances or energy levels outside the nucleus. And what he felt was, as they are excited and heated, the electrons jump to a higher energy level. So the energy shells, the electron shells closest to the nucleus are lower energy, and the ones further away are higher energy. And you give those electrons some energy, they get excited, jump to a higher energy level, and as they fall back to their original level, they emit light. So you can see here, this electron, the atom's been excited, the electron jumps from the first energy shell to the third, and once the energy source is taken away, the electron falls back to its original position, and in doing so emits some light. So this proved evidence that the excited electrons were giving out light, and then different atoms gave out different wavelengths of light, different colours of light. And finally, the neutron. This was James Chadwick. He proved it. So we already knew about the neutron. Scientists had said for years that there were 2 subatomic particles in the nucleus. They knew about the proton, but they didn't know about the neutron. But they just didn't add up. And this is why they knew it was there, because they knew how many protons an atom would have, but the mass or the weight, the atomic weight, didn't add up. So Chadwick was the person who did the experiment that proved what that missing mass was, the neutron. And what he did, very similar to the alpha scattering, he fired alpha particles, but this time instead of gold foil, it was at beryllium and boron sheets. And what appeared was this strange radiation. At first it was thought it was gamma radiation, but actually it was the neutrons. So he'd proven that, yes, what scientists thought for years was indeed true. In the nucleus, as well as protons, there were neutrons. Okay, so what I'd like you to do, hopefully that's between your research and looking at this, you've got enough information there and you understand how those models of the atom have developed and how we've come to know more detail about protons, neutrons and electrons. I'm just going to put some questions on screen, and what I would like you to do, again, just spend a few minutes, I'll just move that, just spend a few minutes looking at those. Have a look at them. I'm not going to read them out. I will leave them on screen there. So if you want to pause the video now, it's just a little bit of comparing and contrasting the different models. And then in about sort of 10 minutes, if you come back, press play again, and we'll go through those. Okay, we'll take these one at a time then. So the first question, the type of evidence that leads scientists to change their model of the atom, it's all about experiments. It's a very generic exam style question, this. They like to ask what type of evidence, and all they're looking for is experimental evidence. The fact that we're scientists, we do experiments, we come up with models, and we look at differences and we see if we can improve or change a scientific idea or construct. Next one, state 2 differences between Dalton's model and the plum pudding. 2 key differences. Dalton just referred to spheres for each atom with no other parts to it, whereas the plum pudding model does talk about these negative charges put in the positive sphere. Number 3 is a very big exam favourite, looking at differences between atomic models. It could ask you differences between the nuclear model and plum pudding as this one. It could ask differences between what Dalton suggested and what J.J. Thomson suggested. So the wording will be slightly different, but the idea is still the same. You are looking at atomic models and looking at the differences between them. So for these two, plum pudding suggests a large sphere of positive charge, but nuclear model has the positive charge in a small area in the nucleus. Second difference, plum pudding model's got electrons stuck in the ball of positive charge, but nuclear model has electrons in shells. And finally, the plum pudding model has no reference to protons or neutrons, but the nuclear model does. Again, number 4, we've kind of covered this several times, this plum pudding model with the large sphere of positive charge with negative electrons sticking into it like pieces of plum in a plum pudding, or pieces of blueberry in a blueberry muffin. And finally, the Rutherford scattering experiment. Now, as I've said, it was Rutherford who was in charge of this, and he set Geiger and Marsden the task of finding out this. So you'll see it referred to as either. But the idea, positive alpha charge particles were fired at gold foil, and what it showed was many of those alpha particles passed through. Some were deflected and some were reflected, and it proved that a lot of the atom is empty space and that the positive charge is concentrated in the nucleus. So because the alpha particles are deflected or reflected because of their positive charge, they pass too closely to the positive nucleus. Okay, to finish then, what we've got here is a past paper question. This looks at different models of the atom, and this is the sort of thing you might see in a GCSE exam. So we've got 5 diagrams that represent models of the atom. Now, in terms of this question, there's a couple of ways to look at it with an exam question. You might look at a model and see if you can identify it before even looking at the questions. So straight away, my eyes are drawn to B, because I can see it's a big positive sphere with little bits of negativity. So I can see that that is the plum pudding model, and I can see straight away A, which diagram shows the plum pudding. So I might straight away for answer A, I'm going to be ticking box B, and if we check the mark scheme, you can see that that's correct. I can discount D and E as answers because D is just showing a sphere. Now, this is what Dalton said right at the start of all this. So if none of these are referring to Dalton's model, which they aren't, I can get rid of D. The reason I can get rid of E is because it's the opposite of the plum pudding. This is made up. This is just to try and confuse you or to put a little bit of doubt. So when you sat in an exam, you might think, oh, is that plum pudding or is that, well, it's got bits stuck in it. But we know it's positive with negative stuck in it. So all I've got left is A and C. So if I look at question B, which is the alpha particle scattering experiment, it's got to be A or C. Now I'm drawn to this one purely because the nucleus only shows positive charges. It doesn't suggest anything else is in the nucleus, and that is what the alpha particle scattering model showed, that in the nucleus all you have is positivity. That's all they knew at this time. Nobody knew about the neutron. They just knew positive nucleus concentrated at the centre with electrons around the outside. So this suggests to me for answer B that the alpha particle experiment is C, and now we can see the correct answer. Which must mean, if this is showing Niels Bohr's work, it must be diagram A. Now this is also one that you can work out by process of elimination, because Bohr suggested that the electrons were in specific energy levels or shells. And at this time, they also knew there was something else in the nucleus, but they didn't know what. So this ticks both of those boxes because it's got the extra bits in the nucleus, and it's also got electrons in very specific shells or energy levels. So again, the model from Bohr's work has got to be A, and there we can see A. And finally, this is a bit of an interleaving question, working on mass number. So it's something that you've looked at before, not necessarily covered in this presentation, but it's just refreshing your memory. Define the mass number of an atom. So the mass number of an atom is basically, it's the sum total of all the protons and all the neutrons that are found in an element. Okay, and it's in the nucleus, so we can see it's the sum of protons and neutrons, or it's the number of protons and neutrons. Word of caution, you must mention both protons and neutrons for that. Okay, again, it's only 1 mark, but these are little marks that people may tend to lose, which will reduce their exam performance. So, to summarise, As part of this presentation, hopefully you've got a better understanding of the models of the atom, how those models have developed over time, from Dalton's very, very simple idea of spheres, progressing through to the idea of the plum pudding model and positivity and negativity in charged particles, then a better understanding of the proton being in the nucleus and electrons being around the outside, and finally coming now to modern times, knowing more about the neutron and this full nuclear model with full ideas about protons, neutrons and electrons and where they are found.